Hey Aditya, hey Kishore.
Hey Ravi.
Hey,
Hello.
hello.
Hey Ravi.
Hey Kishore. I'll make you the host, Kishore.
Sure.
Done. Hey Ashish, welcome. Hi Vineet. Hey Vineet, you able to hear me? Ashish, we're on audio. You can disable your video, please.
ఎందుకు
Yes, Ashish. You're not able to hear you, Ashish. I can see your lips moving though. I think disable the video. There's no need of the video now. Yeah. You're muted, Ashish. Just unmute and then speak up.
Hello. Hello.
Yeah, I can hear you now.
Yeah. When will start?
We're going to start in a minute or so, Ashish.
Okay.
Kishore, can I request you to start off, please?
Sure, Ravi. Okay. Ravi, can you give me the control or make me the host? Or I am the host?
You're the host already, Kishore.
Okay. Yeah. So, good afternoon, everyone. So here we are again for this talk. Thank you for joining again. So let's do a refresher about what we spoke yesterday. We went through all the basic network topologies, um, how they are connected, why they are useful, what is the best way to, what's the best topology we should use right now. So I think I should ask you a question. Probably Harshal, you can tell me what is that? What type of topology do you think you have at your home right now? Can you hear me, Harshal? Or Aditya, you can tell me what type of topology do you think you have, network topology do you think you have at your home right now?
I think it's bus topology, Kishore.
Why do you think bus?
As I'm the only one connected to the router, So I think it's a bus. But where the router is residing, I think it's maybe star topology or mesh topology over there.
Okay, okay, that's fine. Ashish and Vineet or Harshal, anyone? What type of topology do you think you have at your homes right now? One?
Not sure.
Okay, so that's, I think, should be a star topology. Just because you have all your laptops, desktops, mobiles, tablets, even TVs, or fridges, everything is connected to your Wi-Fi router only.
Only
That's-
Wi-Fi. Only
Yeah.
Wi-Fi.
Only Wi-Fi router, yeah. So that's the reason it's called a star topology. I think Aditya, you got it right on the second try. So your topology is everybody uses it in star because that's where it connects to out. So we all, my device is like, that's the center point for me to contact, and then it still caters to
Yeah.
all the devices at any given point of time. It doesn't say that, you know what, your TV is used, I'll not provide you internet connection. That doesn't happen. It still provides you the connectivity no matter how many devices are connected. Correct? Yeah.
Okay.
So that's
And
go ahead.
hello. Sir, and when in a company or a large scale means in big multinational company.
Yeah.
Yeah.
It's again a star because you have your client server models where you have desktops as clients and server as a central point of contact.
Means
What happens is in your office itself. So so we have to take, I think, we have to go to very beginning of how the network is set up. You have something called as LANs, you have something called as WANs, you have something called as MANs, right? So LAN is local area network, MAN is metropolitan area network, and WAN is wide area network.
Wide net. Okay.
Yeah. So LAN is nothing but within your own building, right? So within your own building, you mean you will be connecting to a switch or a router, and that will talk to a server intern. Correct? So your LAN becomes a star network, and your LAN will talk to a wide area network or a MAN, which is metropolitan area network, which is connecting one city to the other city. The MAN, metropolitan area network or wide area network, will talk to two different offices in the same city via internet. So your one office will connect to the internet via MPLS, which is multi-port links, which I think I am not sure what the abbreviation is, but that will allow you to connect to the internet using that link, and that is a dedicated link which the service vendor or the communication provider or telecommunication provider provides you to connect to your other office. So you will use this type of technology to connect to a WAN, wide area network. But when you have your MAN, WAN, and LAN, right? So local area network, wide area network, and then metropolitan area. So the metro is nothing but two cities. Then again, it will also be that you are using your internet to go out via VPN, and that VPN connection will get established with your other office in the other city. That's how two different cities are connected. Even though you're sitting in India, you're still able to access your US server is because it's connected through a VPN, virtual private network.
Virtual private network.
It's done up through the internet, and say that there is at the end of the network, or in US, there is another VPN server which provides connectivity to the US network. That's how you're connected to that network, right? So though it looks like client server model, it will always be a star, more or less a star. It will not be a mesh. Mesh, yes, but again, mesh will not be commonly used. I wouldn't say it's extinct right now. Though in the same office, you will have, let's say, suppose, primary example, you have a research facility, like R&D medical research facility. Do you think your procurement or finance will have access to the research and development network? Never. So that segment is completely different, and the other financial department, HR, IT ops, everything is different. Because if you provide access to the network, so since you are isolating the research itself, nobody else can access that particular segment and connect to other machines. That's how you segment your network, where you're telling that this set of IP addresses will be part of one subnet, which is say that R&D, and nobody else will be able to connect. If you are supposed to connect, you need specific access, or you need to connect to one router, or your route needs to pass through one specific path where you will get authenticated, or you will need credentials to access. So that's how you segment, and then you make sure that you are connecting to one point of contact, which is a switch or a router, which differentiates like parts of our network, right?
Okay. Thank you.
Perfect. So let's move on. So we were talking about OSI layers, right? So just to make your life simpler, I know you all understand OSI layers pretty much. You would have learned a lot about it, but again, a refresher never hurts. So your OSI layers on the image on the left hand side, let's go through that. I think that gives you a pretty much decent idea. The first 4 slides, or the last 4, I think transport, session, presentation, and application is the responsibility of the host, because it means if you're using a browser and if you're trying to access an address or something like that, or stream video, your browser will need to do the job of controlling application, presentation, session, and transport layer, right? And then the network data link layer and the physical layer is the responsibility of the ISP provider or the network itself to take care and make sure that that communication goes through to the endpoint. Make sense? Good. So then if you see on the right hand side, that's where we give a high level definition of each layer. Let's come to physical. So physical, we understand if you see a network cable, a CAT cable, we understand what is that. If you see a Wi-Fi router, we understand that. We switch these. If you guys have seen a switch room or a router or something like that, you know what is that, right? A Wi-Fi router or access points in the offices, or in your bus terminals or railway stations or airports. You'll see all this physical infrastructure out there, right? That's your physical medium. And you have your data link layer, which is more or less saying that, I will try to make sure that your data is getting through without error, and then it's transmitted on the network. Then the other layer is the network layer. This layer is responsible for moving your packets from source to destination, right? So where it needs to go, who it needs to do. You can actually say that network, data link layer, and physical would be the responsibility of the post office. Like yesterday we did an example of me sending out a letter. So that's where it is. Like, the post office or the post office infrastructure is what responsible for ensuring that it reaches without any problem and doesn't get routed to a different city, which is not the actual address, right? Then we have transport, which is ensure that reliable delivery of messages from process to process, because that's how your 2 different processes are talking about, right? And then session is all about establishing a session, maintaining a session, closing a session, and then making sure that session is still established, and then it's always random, or it's not being disrupted. Then you have presentation layer, which is more towards translating the content, compression, and encryption. Right? That's how the message, that's how the layer works with the presentation layer. That's basically supporting the application layer. The application layer provides the actual services to the user. So suppose I am using the Zoom video. Zoom video itself is working on the application layer, right? So there is some layers, in applications working in the background. Then the application layer takes control of translating the content, which is understandable by both the sender and the receiver, and by the operating system itself. Then it also what does it once it does a translation of data from understandable medium to the application layer. For the lower layers to send the data, it also does the encryption. It compresses the data and encrypts it and then passes through. So why do we compress and encryption? So when you compress a file, the size of the file reduces. It's easier for me to send that file across the network, and then when it's getting decrypted or decompressed, you'll receive all the data back. right? It means for me to send across the data in a much efficient manner, I'll try to compress it, and to protect the data, I'll try to encrypt it, right? Cool. Moving on. So this is some animation which you might see it interesting. It means like, the application presentation and session layer does everything. You get the data, it moves to the transport layer adds its header, then the network adds its IP, the data link layer will add its frame, the Ethernet frame. Then it goes to the physical medium, the bits and stream. It does the reverse of it. It understands what the Ethernet address, then it understands what the IP address is, then this was the destination, then the transport layer will understand what the TCP flags are, and then the data gets passed on to the session presentation and application. So whatever it happens in one way happens the other way around in the other layer there. Right? Cool. Moving on. So for you guys to understand easily and then remember the OSI layers or the app, these 7 layers easily, would be to say that all people seem to need data processing. A, application, presentation, session, transport, network, data link layer, and processing, or physical. Right? So always remember that your application, even now, probably that's some of the interview questions you'll say that, what's the 6th layer, what's the 1st layer? People get confused in the 7th and the 1st layer. Sometimes people say application is the 1st layer and the data link physical layer is the 7th layer, but it's not. Physical layer is the 1st layer. So you have to go through physical data, network, transport, session, presentation, and application. But if you want to remember all these things, application, all people seem to need data processing, right? Then let's look at something called as protocol data units, which is nothing but how each layer would try to segment or understand the data, or add its layer of information to that particular information which is coming across to that particular layer, or that number of that layer. So OSI layer, each layer adds a header containing protocol information specific to that layer, right? That simply means you will have, so if you look, the header is nothing but you have, say suppose you're sending out an email, or say suppose a video or something like that. So that's your data, that's your thing which you want to send across. So what it does, application layer or the presentation layer would add its own header. Like, okay, this is a presentation layer. So what does that presentation layer does? It helps in compression, it helps in encryption, and it helps in translation. So what type of encoding is being used in presentation layer? What is this type of data which is getting transmitted? It will try to add that part of information to the packet, correct? Then what happens, or to that particular data, like that before the data, say that okay, this data is all about sending video streaming data. So the encoding mechanism or the translation, how do you understand this? It's a video or MP4. Okay, and then the session layer understands, okay, how do I need to set up a session? What is that required for a session? My source and destination, and then what type of session IDs do I require? That's all from the application of the presentation layer, or the session will say that, okay, now my thing for the session layer, so I will add a session indicator saying that this is the session ID for the communication which is going to happen right now. So the session is done. Then when it comes to transport, your transport layer, so your transport layer, what it does, it adds segments. So segments is nothing but, so let's say, probably I'll explain you more as we reach up to segments, but I'll not talk about it right now, but segments, packets, frames, and bits, I'll explain you in detail in the next coming slides. So you have transport for segments, network for packets, data link for frames, and physical layer for bits. So as you saw in the other slide here, so your stream of bits, whichever you see here, is a stream of bits. right? Physical medium is nothing but sending a stream of bits to the other endpoint. So let's talk about physical layer. So physical layer is nothing but controlling my cablings, and then it's all about transferring raw bits on the physical medium, right? So all you do is you need to have cabling, cable connectors and receivers, NIC cards, wireless radios, hubs, switches, routers. It's all your physical layer. It all works on the physical layer, right? And then your protocol data units are bits. Your bits is nothing but physical layer coordinates the functions required to carry bits upstream over the physical medium. As in the layer is in the diagram which you see here, so you get the data from the above layer, which is the data link layer. So that sense it, the physical layer will actually convert the data from your, from your, however it's coming as part of your, how do I say, frames, and break them into digital signatures, which is zeros and ones, right? Your digital signature, which is the digital signature, like the square up and down, or whatever the signal. So that's how it actually converts that into electronic pulses, which will go through the medium, and then the other person at the other layer, with the other physical layer or the receiving end, will actually decode these bits of streams and sends it across to the data link layer. So the physical layer is responsible for movements of individual bits from hop, node to node, which is one point to next point. So, okay, what I want you to do right now is, can you all open your command prompt, do a Windows plus R. You'll see something called as run, right? Okay, so then you type CMD. Once you all get that, type tracert, TRACERT, space, and then type www.google.com and hit enter. Like something like this, right? So what do you see here? You are typing tracert, and then you're saying go and find out google.com. So basically trace the route for me. How am I going through the tracert? So you can type /4 for only IPv4 addresses. That's so that it will be easier for you to understand, or else you will try to see your IPv6 here. So now you are seeing that. Now compare this to this. The physical layer is responsible for moving of individual bits from one hop to other hop. These are the hops which you're seeing here. Each individual hop, right? So my packet or my ping or my tracer says that I need to go to my router, which is this one. Yes, I went to it, and then from here it goes to this route, it goes to this route, it goes to this route, and then it's still waiting for the other routes to go. And that's how we are sending one hop to other hop. So there are also, this is also sending stream of bits from the physical layer to the other hops, to the nearest hop, whatever that is. So guys, if you have any questions, raise your hand. If not, then I'll continue. Perfect. Let's move on. So now, so its physical layer is pretty simple. So it's just bits. So physical characteristics of physical layer would be representation of bits in zeros and ones, your data rate, your physical topology, and your transmission mode. Like you are doing how do I say, you're doing a full duplex, simplex, multiplex mode is what you will try to look for here, how you're transmitting your data. Moving on. So next is the data link layer. The data link layer is nothing but packages the higher layers into data frames. So you might say, what is a frame? So frames are nothing but So whenever you receive some data from your above layers, it gets chunked or divided into frames. Each frame will be sent across, or this data is broken. The frames is now sent out. Each individual frame is sent out along with the proper headers and to the next layer, which is the physical layer. For that, it converts into bits and it sends out. So you cannot send bulk of the entire data in one shot. So what does the system do? The Osi layer does is it breaks the entire data into small pieces. At data link layer, it's called the frames, and each frame will have something called as a physical destination and physical source and destination address, which is a MAC, media access control. So you said, how do I find out? Let's do IP config. So where is my MAC? Nope, I'm not. So I'll do it /all. So my physical address. This is my physical address. This is my physical address, and this is how it will add it, which was a source who sent out, and it will capture the physical address of that particular NIC where the information was coming out from, right? So you use ipconfig /all, ipconfig /all to figure out what is the physical address of the NIC, network information card network information card on your PC, and what does it hold for. So a tip for you guys, you can actually find out which is the company which made this NIC, or the NIC card basically. So what you do is you can search for something called as NIC identifier, or MAC identifier, MAC identifier. So when you put this MAC identifier in that site, it'll identify what is the actual manufacturer who created or who manufactured this particular NIC card. So here I can see Ralink. Again, on the website also, it will tell you that this is done by Ralink itself. So MAC address is crucial for you to identify which type of device it came from. So again, just drifting away from the topic, your MAC address will also, if you're investigating where the traffic came from, it will be useful for you to find out if the traffic was coming from a mobile device, from a tablet, from a Mac device, from a Windows device, from a hardware device. So you'll be able to clearly identify which was sending in. Because if you connect your phone to your this thing, you'll be able to find your phone's MAC address as well. And if you search for that, it will clearly say it's a OnePlus 2 or OnePlus, Samsung, Nokia, or whatever that is, Motorola's MAC address. So MAC address has some importance. Don't disregard it as not useful information. Okay. So ipconfig /all will provide you the MAC address, and that's where this frame will add the MAC address of the source and the destination. Right. Okay. So then move on. So most common MAC address is the Ethernet MAC address. That's what I showed you. So what happens at data link layer? So data link layer is divided into two parts, which is logic link control and media access control. Logic link control is nothing but it takes care of the logic control there. The flow control, the error control, deals with the protocols, what's coming in, how the protocol should be represented, how it should be converted, how the flow of packets should have happened, of the flow of the frame should happen, when it receives an error, what does it do, how it should resend the frames, and then it takes care of everything else. The media access control does is, it talks to the logical access control and says that, okay, you know what, you give me everything, you pack everything, let me control the actual flow of converting it to sending it to the physical media, right? So data link layer itself has two components. One component talks to the upper layer, tells that, okay, this is what I'm going to do for you. I'll understand, take care of everything. The frames are all pre-built. The source address, the MAC address is all added. Let me now give a flow control as to how the data needs to travel, and error control when these frames are crashed, when an error is received, how do I react about it? The media access control takes that information and actually passes that on, converts that entire data, or helps physical layer understand how can it convert everything into zeros and ones. right? So the protocol data units is frame, as I said, yes. The framing, addressing, error control, flow control. So as I said, the MAC media access control address has got originally unique identifier, which is the company identifier, and the network interface controller, which is the actual address for the MAC controller. So this, the other image which I'm trying to point out now will be the information comes from the network layer. The data link layer will add the headers, the frame information, the front and the back, the MAC address, and then it will send out to the physical address. Similarly, on the other part, the packet, when it receives by the actual receiver, the physical layer sends it to the data link layer. It understands, okay, what's the source and what's the destination MAC address, and then it pushes the packet up to the network layer. Okay. Now the network layer. So network layer is responsible for source and destination delivery of packets. So the PDUs or possible data units, protocol data units is nothing but your packets, correct? So network layer actually segments the data in packets so that the data can be transferred based on packet by packet, which is again, breaking the entire data or the amount of information into smaller segments for easier transportation across the network. So network layer ensures that each packet gets from point A to point B, from original to the final destination. But here in the network layer, it will be IP address, right? The network layer is responsible for delivering of information, delivering of individual packets from source to destination host, right? So what the PDUs are, it's called packets. The responsibilities of network layer is addressing the devices and network, populating the routing table and routing static routes. So what does you might say, what is routing table? So every router or every system will have a defined set of routing tables, right? So routing table is nothing but it keeps a list of the nearest source and the IP address. Okay, if I am trying to go through a route or like my router is trying to go through a particular route, say suppose it will go from my router to the nearest hub. From the nearest hub, it will go to the central hub of the ISP. From there, it will go to actually hit the ISP. And then from there on, it will go to the nearest international ISP, whichever is connecting to my ISP. That route is remembered by the routing in the routing table, so that it quickly identifies and calculates which is the fastest route which it can take to send the data across, right? Then it also, this network layer will also be looking at incoming and queuing of incoming data and then forwarding it to the constrained service constraint to this packet. So like, if I'm using video, I don't want my video to be lagging. So it means video get higher priority. So it queues data, and based on the priority of that particular service constraint, it will try to forward and cater to that particular protocol or particular to that service, right? So if like we are talking, it's a live streaming, yes, it will get more priority because the quality of services needs to be more higher than email, right? So when you're doing email communication and then you're doing video streaming will take more priority because you will need to have and then your network cable or your network layer will actually take control in terms of sending or ensuring which will get the more priority first and then more bandwidth first. And then it takes care of the internet between two different subnets, delivery of packets to destination with best efforts, providing connection-oriented and connectionless mechanism. So this network layer will be the one where TCP and UDP will come into the picture, right? So yeah, so what happens, the network address is the IP address. The IP address can be unicast, multicast, broadcast, or anycast. Unicast is one destination, one host. Multicast, destined to a group. Broadcast, I'm broadcasting to you all. Anycast, destined to near one. So in this image which you're seeing, so it says every PC is connected to a router, this one here, and it says it actually broadcasts the data here. So it says, you know, I am 168, 192.168 1.10. It says 162, 192.168 1.20. And this guy says, hey, you know what, everybody, this is my IP address. I am 192.168 2.10, and this guy is 220. So router will take this broadcast and then broadcast this to these guys, so that these guys will understand, okay, who is connected to my nearest network, and then who can provide me DNS, DHCP, and all this type of typical networking services, right? So broadcast is nothing but, imagine broadcast, you don't understand what broadcast is, simply say it's a public rally. So entire public is listening, but one guy is talking. That's broadcast, right? TV broadcast, radio broadcast. It's only one-way communication. The sender doesn't care about where he's sending information. He will just send out his information to everyone who can listen and capture the data or listen to that particular thing, right? Okay, so guys, I'll stop here for a second, and let me know if you have any questions. Perfect. I get this as no questions. Moving on, the transport layer. The transport layer offers peer-to-peer, end-to-end communication between two processes and remote host, right? Then you have your transport layer as connection-oriented. Connection-oriented is nothing but, that particular connection-oriented is nothing but you're trying to ensure that the connection is established, it's not disconnected. The connection is always alive. Like, this particular video chat here, or the presentation, or your chats or WhatsApp, right? It's a connection oriented. The moment the guy goes away, he'll show you'll not see the word online under that particular name. It means the connection is always on, and it's constantly looking out what you're doing, if you're using that application and you're not using that application, right? So the transport layer is responsible for delivery of messages from one process to another. So the protocol suite, the TCP/IP protocol suite is where it comes here. So you have this TCP, which is a connection-oriented protocol, UDP, user data gram protocol, which is connectionless. So TCP can be protocol HTTP, which is 80, nothing but you're browsing the session, or 443, which is more or less saying that, yeah, you want to browse a secure website. And then you have your UDP, which is nothing but your DNS communication on port 53, where it doesn't require to know what is going on. So if you see, the TCP has something called a three-way handshake, right? So before it connects to a destination, it goes through a handshake process, right? So the first time, if I am the sender and you are the receiver, my machine will try to say to your machine that, hey, what? I am trying to connect to you. I'm trying to synchronize with you. So then your machine says, okay, the communication is now coming on port 80. Yes, I'm allowed to accept it. Yes, I am okay to sync with you. And here is my connection, or here is my acknowledgement for your request. Then the receiver, or me, who was the actual initiator, receives that synchronization and acknowledgement request and says that, thank you very much for your acknowledgement. Now this is my acknowledgement for the acknowledgement which you have sent, that I have understood that you are agreed to communicate with me, and from there on, my HTTP request or my communication starts between the sender and the receiver, right? So three-way handshake is the most important thing which you guys will need to understand from a logical standpoint and from a conceptual standpoint, that you need to understand TCP/IP actually goes through a three-way handshake. This will be a common interview question everywhere you go, and this is, and they might ask you a question: why do you think the TCP will go through a three-way handshake? Primary reason: connection oriented. It means the connection has to be established all the time. The sender and receiver needs to ensure that the connection is always established, and so that communication, the data flow can happen even if the session is not active, right? It's a connection-oriented protocol. Similarly, UDP, it's it's like basically saying that, okay, I am not interested in trying to keep the communication with you, but the only thing is I'll do a burst communication. okay, I have a question, I'll post it and I'll forget it. I'll not even be worried about whether it received by you or not. So let's say suppose your DNS. So if you all know how DNS, domain naming services, actually work, it's nothing but it's trying to query any website. So when you type google.com in your browser, it actually hits your DNS server. So DNS says, I don't understand what is google.com. I need to find the IP address for google.com. And then what it does is, what it does is it's talk to your nearest DNS ISP server and sends the communication to it, and just forgets about it. When the receiver receives it and identifies that this is the IP for google.com, it will just send it back. Your DNS server is not worried about connecting to the other DNS server and waiting for his information. Similarly, in this example, you have something called as syslog communication. Syslog communication is mostly used for communication between like a log source, like, how would I say that? So it's like a data repository. So every time what you do is, let's say suppose you have your Windows machine and you have some logs on your machine. Like if you're using your system and then you're clicking on something, everything gets recorded. Every network connection you do outside gets recorded, right? So all that information gets stored on your machine. Let's say suppose you want to store it in a remote machine, you will use syslog as your communication channel on port 514. And what happens is, it does is, okay, every 1 hour I'll schedule a syslog communication. I'll send out information to the remote server and then forget about it. That's how UDP works. It's not worried about whether the UDP server or the syslog server actually got the information or not, or what was the error or not, right? If he receives the UDP receives an error, it does a retransmission. If not, it completely forgets about it. So a TCP UDP header will look something like it. Like, both TCP and UDP header have got 16-bit of header each. So here you have a 16-bit header, here a 16-bit header, 20 bytes of TCP header, and I think 8 or 5 bytes of UDP. The total size of the UDP header is 5 bytes or something like that. So a UDP header will have multiple parameters or multiple things, which is source port, destination port, sequence numbers, acknowledgement numbers, your data offset, flags, window size, checksum, urgent, and options. So these are all different parameters for the packet to understand where it's coming from, right? Yeah. So what happens is, so when the data actually comes through this particular layer, so it adds the source port, the destination port. In this case, source port can be your machine's port, any number of port, and the destination port can be port number 80 if you're accessing google.com, right? And then look at sequence numbers. Look at the acknowledgement number. The sequence number is because when I say that your data gets divided into different packets, each packet will have a sequence number and then an acknowledgement number as well. And then the rest of the flags of the TCP, saying that it's an urgent flag or it's a sync flag, what type of communication is going on, and it's the window size, like how much long do I think I'll be alive, and the urgency of the packet and the other options. Similarly for TCP, UDP, this is all not required. It will have a source port, destination port, checksum, and the length of the packet itself. And that's pretty much it. It will not add anything else in that because it's not trying to establish a session. So how you can use this? Let me yeah, sorry. So this is Wireshark. Let me open up Wireshark and I'll try to capture some packets, okay? So this is all the communication which is going on through my machine as of now. So let's say suppose I take a TCP protocol or TCP packet and I want to do a TCP. Oh, this one. Open this up. I'll open a TCP communication like this one. So now I have a frame. Remember where frame comes from, where your frame comes from, data link layer, right? It adds the encapsulation, it adds the capture length, the frame length. Then you have your Ethernet, right? Then you have your Ethernet address, which is your MAC address, right? The destination, the source MAC address, right? Then you have the IP protocol, which is an internet protocol. Again, the source IP, destination IP. Where did we talk about source IP and destination IP? We talked about here in the network layer, right? IP address. So you have your IP address here. You have your flags here, right? Reserved bit, do not fragment. It's a whole different thing altogether when you look at a packet. And then you have your source and destination. And then the actual TCP layer is the source port, destination port, port 80 and this one. And the flags of it, right? So sync, reset, push, acknowledge, urgent. So it says an acknowledge. This is an acknowledgement packet because it shows the 1 here, right? My window size. And then window scaling, checksum, and then options, whatever options I have provided here. And then the sequence analysis, sequence flags. So these are all as part of one packet, which you see, just a single packet which is going out there. And that much information you'll capture it by just looking at one packet itself, right? So guys, Wireshark is a beautiful tool which you should try getting your hands dirty with. Install Wireshark on your machine. So this is my HTTP communication. If I just type HTTP there, you'll get it. So, okay, yeah. So this is how my packet looks like. My HTTP packet looks like, right? How do I do it? You know, I'm trying to talk to this particular page at ftp.hoodson.org, and this is my URL, right? And this is all the content which is going on, because this is a HTTPS packet, right? And that's the reason you're not able to see anything here. So how do I say it's HTTPS? Okay. No, it's not HTTPS, but I think it's a sequence packet, which is where the content is garbled, or my system cannot understand what the content is. So now I'm looking specifically at port 443 communication. This is all how the 443 communication will look like, a garbled content. You can decrypt it only if you have a decryption key. It's all encrypted. So, where is that? Yeah, so that's how you get your TCP header and then your UDP headers, right? So now the responsibilities for transport layer would be service point addressing, connection control, and flow control. So you might say that, you know, how TCP layer actually works, and you know, there are so many things going on. How does it actually does it? So as I said, it does segmentation. TCP transport layer works on the basis of segmenting. Segmenting allows, you know, the traffic from or packets from each of these devices, instant messaging, your multiple web pages, IP telephony, streaming media, to be differentiated in segments. So it will divide your data into different segments, and that segment will get allotted on a bandwidth. Like, okay, if this is the communication channel which is going on, okay, this segment will go now, this segment will go now. It's like a traffic cop, basically traffic cop. Okay, now this side will stop. My right hand side guys will go, and this both left and right hand side will go, and my front and south, north and south guys will go. So that's how the packets get transmitted. They get segmented, and one segments get transmit multiple amount of data in one shot itself, right? So that's how, if you see here, every channel has a color. So if you see the purple is here, your red is here, your brown is somewhere here, and green is here. So it means data from our packets from each of these individual applications gets segmented or put on a package get put on a segment, and then that segments get pushed out, and then it does the next layer. So it basically trying to add in one burst. It's trying to put on a lot of different things and send out the burst across. It's a constant traffic, constant flow of. It's like a traffic cop standing at the junction saying that, okay, now you go, now you go, now you go, now you go, and then it keep controlling it throughout the way. And that's what it uses, is this segmentation of the entire data which comes in. Right? So the how the TCP/IP actually, the whole layered, the whole packets actually work is, as I said in the initial. So when an application and the data gets started from the application layer, it gets the presentation header. So the presentation header will add what? It will add the encryption, compression, and the translation of whatever type of medium it's trying to send across. Then the session layer will add its header along with to the current presentation header plus the data itself. Transportation layer will add the what? The source and the destination MAC address along with the current address, the source, session header, the presentation header, and the data. The network header will add the IP address to the current transport header, session header, presentation header, and the data itself. The data link layer will add its header, which is the actual, the flow control, the size of the window, and everything else to the entire length of the headers, and then that gets transmitted into bits on the physical medium, and that gets sent across, right? And when it receives on the other end, everything will try to rip apart every other information. Data link layer will look at this information, take it off. Then it will get pushed up. Network layer will look at the network header information, rips it apart, pushes it up. Transport layer looks at transport header, takes it off, pushes the session header. And that's how the application layer present the data to you, right? So now let's look at, we have spoken about what is a flow control. So what is all of flow control all about? The flow control is nothing but sender does not flood the receiver, but maximize the throughput, right? How do you do that, right? It's nothing but you, let's say suppose, again, traffic cops business. So you are standing in a bus terminal. You have got 1,000 buses. If you allow all the buses to start at once and reach the gate, not one bus will be able to go out. But if you say that the first bus will go at 1 o'clock exactly, and at 1:01, the other bus will go, 1:02, the other bus will go, 1:03, the other bus will go. In between 1:01 and 1:02, 1:0 or whatever the number is, the other bus will come in. So it means you are actually allowing people to come in and go out synchronously, right? This is exactly what happens in the flow control as well. So sender, when I'm trying to, when I am as a sender trying to send more data, the flow control will say that no, the receiver cannot receive this much data. He can only receive this much data. You have to send only this much data, right? So then the sender and the receiver both agree on a standard, the frame of or a standard flow control. Like I can send you this much amount of data so that you can process it, acknowledge it back so that I can send you the next amount of data. Right? Yeah. Then the methods of flow control should be start, stop, and wait, or a sliding window. So the first the image you see here is the sender and receiver. The sender, I am sending a data. I'll stop. I'll wait for the acknowledgement. When you acknowledge, I'll send it again, and then I'll wait for acknowledgement. It's like stop, and wait. The sliding window is nothing but I will at a given point of time, like 1 to 1.5, I'll keep sending the data. and then I'll stop. I'll wait for your acknowledgement, and then I'll again at 15 to 110, I'll again send the data. Then I'll stop. So as the time window slides or the window is sliding, that's how it will be like this. You will exactly know how much time the data will be transmitted and when you can acknowledge, so that the transmission happens in like burst of information. So that's something called flow control. So that sender and receiver both have control on how much data the other person is receiving and whether they are able to process it. There is no point me sending more data to the receiver if he cannot process it within the given point of time. Then you have error controls. So error control is nothing but error control. You deliver a frame without an error in proper order of the network layer. So when the frames receive at the destination without any error, it means the network layer worked properly without any. There was no congestion or there is no jam in the network itself. Not too much communication is given by or sent across, or there is no transparent disturbance on the medium itself, right? So imagine, remember, if you guys having used their telephones or mobile phones 6, 7 or 8 years back, and then if you are standing right next to the radio, your radio will start interfering with you, right? You can hear the disturbance in your radio frequency. It means there was some disturbance in the signal. Same thing can happen with your network communication as well. If you have too much of electromagnetic interference, or there is a lot of collision, or there is too much amount of noise, or there is too much amount of how do I say that, sudden power outage is there, sudden surge of power is there, the data gets, or the frame gets crashed, and they will receive an error. So error detection is nothing but cyclic redundancy checks or sequence numbers, right? So cyclic redundancy check is nothing but, did I receive the actual packet, or was it supposed to be the actual redundancy check? Did I actually receive it? So other packet will have a redundancy check or checksum value, which will say that, okay, this is a checksum value from the previous packet. Did you get it or not, right? Or the sequence number. So what it does is, the sequence number is again nothing but the series of packets will get received, and every packet will have a sequence number. So when you put all the packets in a sequence, and if you see that there is one packet with a sequence number is missing, you'll request for that packet, or your system will request for that packet, saying that, hey, you know what, the sequence number of this packet or this sequence number was missed. Can you please resend the sequence number? Or you can say acknowledgement and negative acknowledgement. Acknowledgement is nothing but when I receive a packet, or negative acknowledgement is, hey, I never received a packet from you. What is going on? Or else timeout, saying that the connection was not able to set up and I got timed out. Can you please resend the communication again? So these are all the ways where you can do an error detection while sending out and receiving communication. So error recovery can be done by automatic repeat requests, is that after a certain point of time, your router or the source or destination will request for a packet and go stop and wait. So that, hey, I never received an acknowledgement from you, or do you think I got it from you? It'll keep asking that question. Can you please send it? Can you please send it? So once it receives it, and then, it'll go back and ask it. Go back and selective reject is like, it randomly selectively rejects a packet and saying that, this packet did not meet my criteria. Can you please resend it? So these are all some of the error control mechanisms of error detection and error recovery mechanisms where your protocols will use, or your communication channels will use, ensuring that the communication doesn't stop and this information is passed on as it intended. Right? Okay. Then you have something called as connection oriented versus connection less. The connection oriented, again, telephone system. Even before you are calling, there is a path which is already set up. Like there is telephone routers, or not cell towers which are already set up. It means the nearest cell tower will take your request forward to the next closest to the tower, and the tower will reach out to the destination address, right? Or it receives the main circuit board's circuit switch number, and that will let you know what is the nearest destination's cell tower is, and then it will route the address to it. Connectionless is a postal system because once you post an address or post a letter, you are not worried about whether it's really reached or not, right? You put the complete address on each letter or each packet, and then the address decides the next hop where to go, right? Um, it again automatically decides, like, should I go to this particular route, or should I go to this route, whether this is easier for me or that is easier for me, and that's pretty much it. You just have to tell him what to you as a if you drop a post in the post box, you will not tell, hey, you know what, go to this particular post office from there to there. That's how the actual connection link system also works, right? So I think this session, this particular deck is done. I think my deck 2 is done. I will start off with my other slide. So I'll stop here. Okay, I've got 7 chats here. Got it. So anybody, I'll stop here now. I'll take some questions, ask a question. No questions? Awesome, guys. You are making my life easier. Thank you. So what we do is now we'll take a 10-minute break. It's around 3 o'clock right now. We'll meet at around 3:13, something like that. Okay? Everybody good with that?
Yeah, Kishore.
Perfect. Thank you very much. Probably I'll be asking questions right now after this session. Since you're not asking me questions, I will ask you guys questions. Thank you very much. All right, guys, I'm back. So let's start. I think we still have got session. Then we have got presentation and then the application layer. So the application and the presentation layer to talk about. You guys are here. I think
Yes,
one more
Kishore.
guy. Perfect. I'm not sure if Kenneth has left. Ravi.
Yeah, I'm just checking with Kenneth, Kishore.
Okay. So you want me to wait for
No, go ahead. Go ahead. I'll
another
quickly
5
ask.
minutes, or do we start?
No, go ahead.
Okay. Perfect. Cool. So now let's look at session layer. So the session layer provided by the first three layers, the services like physical data link and the network layer are not sufficient for the same process. Session layer is responsible for establishing, maintaining, and ultimately terminating sessions between devices, as we all know. If a session is broken, the layer can attempt to recover the session. The session layer is responsible for dialog control and synchronization, right? So the responsibilities of a session layer, dialog control. The session layer allows two systems to enter into a dialogue if it allows the communication between the two processes. So it means nothing but if my my web browser and the web server wants to talk among each other, this is how it will happen. The dialogue will happen during the dialog control, right? These two processes, the processes which is rendered or used to fetch and display pages, web pages, will be the one will be used for dialog control. The synchronization is nothing but allows to add checkpoints or synchronization points to a stream of data. So it's nothing but you saying that at this point of time I'll refresh a page and then reload the entire data or provide you the next bit of information which this source or destination needs to get or receive. Example: if a system is sending 2,000 pages, it is advisable to insert a checkpoint every 100 pages to ensure that the 100 pages unit is received and then acknowledge it independently. That's how you will ensure the session is up and running and it's not been broken. Right? So that's how you'll tell the other person that, hey, you know what? In this session, I got whatever you are sending me. Please send the rest of the information. That's how the sender and receiver will be synchronizing each other. Then you have your presentation layer. Presentation layer is concerned about with the syntax and schematics of information exchange between two systems. So this ensures the data that sending application can be understood by the receiving application, right? So so the primary responsibilities, as I said, translation, encryption, and compression. The translation can happen from, let's say, suppose you're using ASCII or you're using some type of encoding mechanism for your data, or you've written the way it has to get encoded. The system will send the web pages encoded in a certain format. So when it receives on your system, it says, you know what, I am sending you information in a certain encoding format. Please ensure that you have a decoding format on your end, so that when I send it, you are able to decode it and present it to the user, right? So like if it's a base64, ASCII, hex, HTML encoding or binary or whatever that is, whenever you send some type of encoding of data is done, then you'll be able to transmit it, right? When the encryption happens, you know all about encryption. Like it's all about making the data unreadable, ensuring that whoever can intercept the data is not able to understand what the data is all about, apart from the intended recipient, right? Okay, Ashish, you raised your hand. Yeah, you have a question, Ashish?
Hello.
Yeah, Ashish, go ahead.
What is encrypted data and decrypted data? What is difference between them? Encryption and decryption.
Yeah. Okay. I'll show you. Just again. I'm trying to see an example online so that images explains things much better. So in a nutshell concept, yeah, okay. So let me know when you see my screen. You are seeing it, right? So I'll type that this is test data. So I say that I'll be using electrical code block or code block, and then my bit size is 128, and then my secret key is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay.
This is encryption.
Yeah. So and these are all the components of encryption. So this is AES, Advanced Encryption Standard. So don't worry about everything else. Just try to understand how it encrypts. Like what are the components of it, right? And then I say encrypt. Set the length of the key. It should be. Length of the key is 16. Okay. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is the length of the key is 20. So my encryption secret key itself is 20 character long. So then I, how long do I get?
Okay, I think it should be only 16 characters, Kishore.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Perfect. Thank you, Aditya.
Okay.
So now the output is AES says this is the encrypted output. What did I say? This is a test data, right? And what did I got the output? I got the output as an encrypted data. So it means in a basic terminology, it will the plain text will get into a cipher text, which is nothing but this. It goes through a calculation programs by using an encryption methodology by saying the bit size or the key size and giving the key itself, and then telling how the output will look like. If I say hex, the output will look like this. If I say base 64, the output will look like this.
Okay.
Right? This is what plain text, unencrypted data, encrypted data will look like. So now what I'll do is I'll copy this, paste it here, and then paste my key here, and then
secret key. Yeah. Then it will be decrypted.
Yeah, it will be decrypted. So we say base 64, right? AES decrypted. Why didn't it come? Yeah, see.
This base 64 means base 64 means what?
No, base 64 is an encoding mechanism. I'll show you what. ASCII to hex. So I use this site a lot.
Yeah.
So this is test. So this is the basic ASCII format. How the text is getting represented, right? When I say convert, this will perform some calculation. This is the binary code. So THIS has this binary notation, right? The base 64 is this conversion. The hexadecimal is this. The ROT16, URL encoding, HTML entities, decimal has got all this. So remember, everything has got your ASCII. The encoding formats are different for everything else. So even if you think that you can convert this data to this, probably this is an encrypted content because this is not clearly visible, right? I need to use a decoding program to convert the base64 whatever the tag is, or the base64 encoding mechanism to an ASCII mechanism. Right? Makes sense? So this is something which we can talk about later. I'll gather more information and share it to you, how it's used. But usually in your websites, when you're accessing website, you'll see a lot of this information. So if I press, hello, can you guys hear me?
Yes, Kishore. Right now it's audible.
Yeah. Okay. So if you do an F2L on your machine, you'll be able to audit your system. Like, you'll be seeing this one. So you look at the elements, you look at your consoles, sources, and then network packets. Yeah. So if you click this, you'll get a header. So this header is what you will be talking about, your encoding mechanism. Yeah, okay. So content length, content type. You see UTF-8, and then it has all the other things which is talking about. So this is where you'll understand how the data is encoded and decoded. And then you look at a preview, you look at responses, you look at keys, and you look at timings. But the header information is where, when you do the F2L on your Chrome browser, you'll see a lot of this information, which is what your browser is sending out and what is receiving. Right? So you'll see Google.com's, all other different parameters it's going through, and then your header information get the encoding. Right? Accept images only. Language is English US, and whatever that is. The encoding format is gzip and deflate. So you need to deflate the information. Where is the other information? What encoding URL encoded. So this is how you'll see a lot of information being encoded and decoded on your browser, which is sending out the information. Right? So that's how your translation usually happens. Did that answer your question, Ashish?
Yeah.
Perfect. So now let's look at compression. Compression is nothing but you are compressing number of bits transmitted over the network. You don't want to send out large amount of information on the network in one stance, so that the entire network gets blocked. What you do is you compress the content, you encrypt it, and then you send it. If you compress it and then you don't decrypt it, somebody else be able to capture all the data sequence of packets and then put it together and say that decompress the data and then look at the data, what's going on. Similarly, what you do is you first encrypt the data, then compress it, and then send out. So it means when you compress it, the amount of data which is there, the actual volume of data gets compressed, and then you break the data into smaller fragments and then send out. And remember, just a second, guys. I think I have a problem in this. Okay. Yep. Okay, let's go. So that's how it happens. So when you encrypt data and then compress it and then segregate into chunks, it's get harder for the interceptor or the man in the middle to intercept the packets and then gather the packets and then try to understand what's it doing. The other thing which the router or the physical device does is, when routing the packets, it will not route all the packets in sequence. Like, it'll send 1, 2, 3, 4. No. What it does is it sends 1, then sends 3, then sends 2, then sends 5, then sends 4, or will send all these packets into different routes. So that even if the intercept, the person who is trying to listen to the conversation is on one channel, he'll not get all the packets, thereby defeating his whole purpose of somebody trying to intercept it. So the presentation layer usually includes like text, the rich text format, ASCII, then images, GIF, JPG. Question for you guys: what is JPG stands for? JPG is an abbreviation.
It's just JPEG, but I don't know its abbreviation.
Yeah, JPEG is nothing but joint picture group. So that was a group who actually created images.
Okay.
GIF is nothing but graphic interchange format, the GIF animation. So these are all small things which will kind of, say aha kind of moments, right? So
Yeah.
just try to poke around, try to get as much information. MP3s, WAV, MPEGs. Again, this is also MPEG is a motion picture expert group or something like that. MPEG.
Okay.
AVI, movie format from Apple, right? Then we have when we get the last
application.
Then we get the last 7th layer, which is the application layer. Again, nothing but it allows me to interact with the software on the network or whatever that is. Right? It provides a user interface and supports the service as electronic mail, remote file access, transfer, everything else. Right? It provides the user interaction. So examples of application: FTP, file transfer protocol, HTTP, POP3, SMTP, Telnet, mail services, directory access controls, your file transfer. So it's more or less responsible for all this stuff. Then summary of all these layers, right? So the application layer allows you to access the network. The presentation layer allows you to translate, encrypt, and compress the data. Session layer establishes, maintains, and terminates. Transport layer provides the process-to-process message delivery, error recovery. The network layer moves the packets from source to destination. Data link layer organizes the frames, adds the MAC address, then the transport at the MAC address, I think, right? And then data link layer organizes the frames, sends out, make sure that the hop-to-hop delivery is done. The physical layer ensures that the data gets pushed out as it's done, like in the streams of bits. So on a very high level, physical layer uses Bluetooth, your USB, IEEE, security, and whatever that is. Data link layer is frame relay, MAC. Energy is nothing. Network layer is nothing but your IPv6 and IPv4. Your transport is nothing but your TCP and UDP. Session layer is nothing but NetBIOS or WinSock. NetBIOS is nothing but your network basic input output. It's a host resolution and ensuring that you have proper connectivity. WinSocket is nothing but WinSocket. It's ensure that the socket connectivity is there. The presentation layer is nothing but MIME or multimedia mail or multimedia internet, something like that, mail extension or something like that. MIME, let me quickly do an abbreviation. Yeah. Ooh. How did I forget this? MIME, yeah, multi-purpose internet mail extension. That's what your email address like. And then the application layer is nothing but HTTP and SMTP, right? This is that's how it's like a representation of what these layers are in a nutshell. Okay.
Excellent slide, Kishore. Comparison between our energy points and
Yeah. Right. Exactly.
Yes.
Yeah. Good. So the other thing is, like, this is again one more good slide, which I think will represent a lot of good information. So you are at the top level as the user. You will use DNS, HTTP, email, SMTP, telnet protocols, the network process to the application. Then the data will representation and encryption, recognize data, HTML, doc, JPEG, everything else. Then it comes to the session layer. Inter-host communication establishes TCP, SIP, RTP type of communication. The transport layer will have end-to-end connectivity and reliability between the routers and the edge routers. The network will have all the IPs, ARP, IGMP, all the protocols. And then I think data link layer will have the fiber optic, the frame relay, SDLC, token ring, and all these other methodologies. And then the physical layer will have the actual connectivity. So another good representation of how do you think you can segment and understand what this layer are, right? So now you might have a question that why am I reading so much about TCP/IP layers? As I said, the more you read about all this, the more you know about how an attacker can come in, and then you'll be able to picture that attack in your mind. If I say that network 3 and network or layer 3, layer 4 type of attacks, then you will quickly say that what is on layer 3 and what is on layer 4, transport and network. The transport and network type of attacks, what does it happen? How does it come in? What protocols are used? What can I find out as an anomaly? And what should I do? Correct? So that's how you will try to put yourself in an attacker's shoe or in a defender's shoe and try to say that, okay, this is a DDoS. Where the DDoS will happen? How the DDoS will get detected? What technology or protection should I keep it in place for an attack to come in at a layer 4 or layer 3 attacks, right? So that's the reason we are so much reading and talking about Osi Layers. The other thing is you have again TCP/IP protocol suite. Again, this is more of a Department of Defense. So the application layer protocol in TCP/IP is a combination of application, presentation, and session layer. The transportation layer is nothing but your host. Your internet is nothing but your transport, sorry, network, and then your network access layer is nothing but your physical and data link. So the TCP/IP protocol suite is compressing the Osi layers into only 4 layers instead of 7 layers. That's pretty much it. So in the TCP/IP layers, you'll see application presentation and session layer, application presentation session layer happening in one. All the related content, decryption, session type of activity happens in there. The transportation uses the SCP or the FTP. Our network will use the IGMP. The physical will use the data link layer and the physical route. Now, it's not difficult. It's not so much different than the Osi, but it's just a combination. They're grouping up the layers to just do common functionality, and then they're not trying to have it, divided and say that, okay, every layer has to do it. So now we will look at the port numbers and IP addresses, right? So the transport layer usually will provide you the port numbers, right? TCP, UDP port numbers. Then your network layer will provide the logical addressing, which is the IP address. Then your data link layer and physical layer will provide you the physical addressing, right? This is, you need to be ensure that transportation layer always provides you the port numbers. Network layer always provides you the IP addresses, the logical addressing, right? And then your data link layer and physical layer will provide you the physical addresses, which is your MAC, media access control, your NIC information. So IP address is a unique number assigned to each computer or a device such as printer, each of them unique identified on a network. So everybody knows why an IP address is used. It's not a strange thing. So let's not talk about a whole lot, right? So IPv4 uses 32-bit addresses, which is 4 billion addresses. IPv6 uses 182-bit addresses, which is trillion, I think, some trillions of addresses which can be used, but it's not in picture right now. Yeah, I don't know, 3.4 into 10 to the power 38 addresses is what it can do. So 34 UDCillion or 34 billion addresses is what your IPv6 is all about. So 344 times billion. So I don't know how many zeros will be in that, but that's how the number of IP addresses which you can assign from an IPv6. So your IPv4 range is, your class A is 0.0.0 to 127.255. Your class B is 128 to 199. Your class C is 192 to 233. Class D 224 to 239, and class E 240 to 255. Right? So if I say class A, immediately you should recognize it's anything stopping at 127 to 255. Class B 128, 192. Class C 192, 223. Class D 224, 239, and class E 240 and 255. So that's how the IP ranges are actually divided, right? Yeah. So now let's look at how your class A addresses get assigned. So in your class A, which is nothing but your 0.0.0 to 127.255, this is your class A. The first octet, the byte 1, byte 2, byte 3, byte 4, your byte 1, so 0 dot or 127 dot, and the rest of the bytes are nothing but your host ID, which is your identifying your machine in particular. While with class B, your first two octets are nothing but your network ID, the other two are host ID. In class C, the last octet is nothing but your host ID, and your first three octets are nothing but your network ID. And class D is multicast, which you can say any to any, and then class E is reserved. It's not yet being used right now, but it's internally for companies. So this is a representation of your class A, B, C, and E routes. Okay. So if you see that 128 actually comes in a class B. So as we said, 128, the first two octets are your network IDs. So that's how it says, my network ID is 128.10. Anybody in that range would be 128.10.0.1, and the router connects to the this range. And anything 128.2.211 is another network range where it connects to which has an IP address 128.211.6.15 would be the host ID, and here 0.1 and 0.2 would be the host ID for this IP address. If I'm using 10 dot, which is nothing but class A, right? It means my first byte or first octet would be the network ID, which is this one. So 0.0.37 is my host ID, and similarly here 0.0.49 is my host ID. But for 192, my class C type of address, what is that? My class C is the last octet is my host ID. Dot 3 is my host ID. 192.5.48 is my network ID. So that's how you represent your data, or represent your routes, or represent your IP address in your segment, in your network. Right? So imagine now quickly what you do is go and identify, do an IP config on your machine, open command prompt, do an IP config. I think I should have. Yeah, let's do IP config. So what's the IP address here? 192.168.29.255. So that's 235 is what my host has got, right? So can I do like this? 192.168.29.5. There a host? There is no host. Remember, you see here, I'm just changing the IP address at the last octet itself. I'm in a class C address.
Class C.
The last octet will represent the host of the host IP address. Yeah, I think we should figure out how do I ping a subnet range. I'll figure that out. Okay, so that's how we will try to understand. Every time you see a 192 or a 128 or 10 dot, you clearly say that 10 dot is nothing but the first octet is the network ID, the rest is host ID. 128 is nothing but the first two octets are my host ID, rest is my network ID, and the rest is my host ID. Anything class C, first three octets are network ID, and the rest is the host ID. And my class D and class E registered, and class D is my multicast IP address, right? So this is what the example. The private IPs are nothing but 192.168, which is what we are using for our Wi-Fi's, right? So your reserved ranges are 10.127.172 and 192.168. So you will not see these IP addresses ever in public, right? You will not see the 10.127, 172 and 192 series in the public used by a public server or any server out there, right? Since these are reserved, you cannot use it in the public domains. But the public IP address can be any other IP address which is not in this range, which is nothing but your 20 dot or 128 or then what are the 172 and from there on, right? You can use that as part of your public IP address assigning. So you might say that, Kishore, we only have some limited IP addresses. Why not everybody has got an IP address? So the magic here is the ISPs will get a set of bunch of IP addresses assigned to them, and they will internally NAT and give them the assign the other reserved IP addresses or range of IP addresses to their routers or switches. So they can use a pool of IP addresses for them, but they will not. But every other user will only get an IP address assigned within their network, and that will get NATed to the IP address of the ISP and will go out, right? So if you can go to a site called what is that? What's my IP? So this is my IP address. It's a IPv6, right? So I can go to this site, and your host IP is 49.37.204.207.14. So this is my IP address. Okay, right. See, ISP is Geo, Chennai, Tamil Nadu, and this is my IPv6 address. And you use VPN to hide your IP address. You use Tor type of services to hide your IP address so that it's not visible to everybody else and figure out what your IP address, where you're coming from. 49.37.204 and 14. So this is your IP address, Reliance Geo Infocom, XYZ, Mumbai location.
Sure.
Yeah.
How are you getting IPv6? I mean, I'm not getting any IPv6 address. I'm getting only IPv4.
Yeah, so I think my router is trying to publish IPv6 as well.
Acha, okay.
Yeah, so that's my router is trying to do that.
Okay.
So
any VPN like that?
No, like the router itself is configured in such a way that to go and do that. So
okay.
Let's look at geo mapping to see where I'm coming from. Yeah, okay. It's showing me here, somewhere in here, but I'm not here. This is probably the hub where the communication is going out or where it's going out. Fine. Cool. So you guys understand the concept, right? Why are we trying to get that, and why are we trying to put public and private range?
Yes.
The IPv6 is an 128 alphanumeric string which identifies the endpoint device on the internet IP addressing. So the example, you have seen that 3.4.10 to 10 to the power 38, which is 340 billion IP addresses which can be assigned, right? But in the current scenario, 2019, you still have a lot of time before IPv4 actually exhausts. And then we all shift to IPv6. So that shifting has not yet happened, but it will happen sometime, probably in a couple of years. So when the IPv4 entire range gets, you don't have any more IPv4s to assign. Okay. So 10 billion people by 2020, next year, each person will be served with more than one computer, assuming 100 computers per person. 10 to the power 12 computers, more addresses per may be required since multiple interfaces per node, multiple addresses per interface, right? So currently what happens is you can have two NICs in your machine, right? So you can attach an external NIC. So you have something called as an alpha card or some external NIC cards which you can attach to your laptop, and then that will become your other NIC where you can configure two NICs to either to listen and to transmit data back. So if two NICs are there, it means you need to assign two IP addresses, right? So it means if you are trying to assign two IP addresses, if a server has the same thing, a server will have multiple IP addresses, a pool of IP addresses per server for one NIC itself. So that's how the system is programmed to give IP addresses to multiple URLs and accept requests for every IP addresses or multiple IP addresses. So that's a prerequisite, or that's the reason why IPv6 is created in the first place. So you have network ports. So network ports is nothing but like your HTTP, SMTP, FTP, DNS, DHCP, RIP, EGRP, OSPF. All these are your ports or port numbers or ports used for communication, right? For running for services. So each of the services are uniquely identified by a number network on the port. So you have how many ports do you have? You have 65,535 both UDP and TCP ports, right? So when I say 198.168.160.125.44:443, it's an HTTPS communication going out to website, right? So in the logical sense, the first 1024 ports are only reserved for widely used services, and rest of them are custom services or custom ports assigned or unassigned, or anybody can use it, right? So that's how the first 1024 ports have been assigned to be used as a common services like DNS, DHCP, and all this HTTP, HTTPS, 25, FTP, and all these things. So some of these protocols and services are like HTTP, example.com, your file services, FTP, SMTP is your mail server, Telnet is, you want to terminal network into a remote host, you can do Telnet, SSL secure shell, you can use that. So you'll have port numbers and protocols. So when you say SSH, and you might ask, why are we having, these many things? What's the reason for this? So every time you want to talk to a particular or transmit a type of data, and that other receiver should also try to understand what type of data is coming and should be able to work on the data. So if I'm sending you text data or web data, you should have an HTTP protocol to encode, encapsulate, and then encode the data and then send it across. There is no other protocol or there is no other program which can do the transmission or encoding and sending it across the network and then decrypting or in decoding and everything else and showing it to the receiver that this is a HTTP traffic and this is how the packet or this is how the web page will look which you requested for. Similarly for HTTP, similarly for SMTP. So a primary example can be you have multiple shops. One person does the bike cleaning, the other guy does the bike service, and then one guy is a sweet shop guy. The other guy, you cannot go and talk to a bike mechanic. I want 1 kilo of Mysore Pak, something like that, right? So he'll not understand. But if I go and talk to a sweet shop guy, I want 1 kilo of this particular sweet. He understands you, and then he'll go prepare that and provide it to you. Right? That's how the protocol also will work. So they understand the type of traffic, the type of requirements, and then according to that, cater the data to you, and then present the data to you. So some of the well-known port numbers, something which you should be remembering, which you by heart, I think, is these ones: the FTP, the Telnet, SMTP, DNS, POP3, SSL, and on this side your TechAX, DNS, FTP, Kerberos. What is that? POP3, SNMP, Traps, something like that, right? Here as well, your SQL, yeah, your yeah, SQL is here 1433, RDP 3389. So you will be able to try and do it. Okay, another demo for you guys. Open up your browsers, type, hold on, I think I already should have it. So open something called showdown.io. So you can type port 3389. So what did we know? 3389 is nothing but your RDP. Where is it? Yeah, remote desktop protocol. So if I click this IP address, oh, sure, no. Okay. So this site is used by most of the attackers or hackers to find out what is open to the internet. Let's do this. MSTSC. I'll have my MSTSC open. So I see this IP address. Yeah, and I can connect to it. Let's say whether this works or not. So it's asking me for credentials. It means the RDP port was actually open. Right? I can actually do an RDP to this one. So or else I can do here IP address. Okay, let's see that. So you see this? It means the RDP was open. So let's do this one. It's asking for credentials. So it means the RDP actually worked. It means the console is taking request. So this is how the request will look like. This is how the pages are looking like. Now you can go and figure out who's actually. So the reason why we say that I'm showing this is not to divert the topic, but saying this the protocol is assigned to type of service which runs on your machine, and then that will provide you other type of information or allow you to communicate with that particular service, right? So let's talk about. Okay, I'll stop here. And any questions from you guys?
Yeah, Kishore. Audit Logs. A small question. Actually, do you have any to know how many ports are in our system? Like while we are trying my like Nmap ports and port and giving our IP, it won't any port. I mean, is there any way to know any open ports in our system, and we need to close those ports which are vulnerable to other sites, like as I said, like RDP and 443 something like that?
Yeah, what you can do is you can definitely use an Nmap.
Okay.
Let me see if this is my okay. All scan ports are on the local IP address. But what I'll do is I'll find out my IP address. Where is that? So what's my IP address? So I'll say nmap 192.168.29. So now it says it scanned my local host from the nmap,
Okay.
right? And it says my port 135 is open, 139, 1443, 445, 2968. What is that? 1990 US admin 8443 HTTP code. All these are open on my IP address, which is my local host IP address. So these are some of the ports which I'm using for different applications. I think that's the reason it's saying that it's a Zeus admin.
Yeah, but my question is, Kishore, I want to close that IPs. I mean, those ports. So, is there any way to close those ports?
Closing the port, I think what you can do is, since the communication will come through your router, you have to do something on your router. I'll figure that out and let you know.
Achha. I want to check between two hosts. I mean, in our Wi-Fi, I want to check between two systems. So I want to open some of the. I mean, is there any way like we need to open some specific without? I
think what you can do is enable some of the services, and that will open these ports. Right? Yes, because these are running for a service in the backend, right? So you need to identify what the service is. If you stop that service, this port will never run.
So it is the only way. There is no other way.
Yeah, I think that's how you have to do it. Because on the firewall, when you write a rule, right, you can clearly say that this port needs to open or this port needs to close. But when you actually on your system, you need to close or open, you need to enable or disable a service. That's how the ports get open or closed.
Okay.
So you need to figure out if I need to say that HTTPS, I need to figure out all the services on my machine. I think I need to run service. Dot yeah. So these are all my services which are running, right? So I need to figure out all my running services, right? If I can go and switch off any of the services associated with any of the other things that's on now, I will need to figure out.
Okay.
Right? So this is called remote procedure calls. I need to figure out what ports it is running on, and then how this is configured. I will try to figure out. I will try to go and say that okay, if I stop the service, that port gets closed, or that's so even the port is open, the service will never be able to communicate with that port.
Yeah. We can get this on the top command also, right?
Sorry.
Top command. What is the process and what is the port? What is the service running?
I think you should be able to get it.
Okay. Sure.
Yeah. More desktop services, right? It's a stop, and that's the reason we do not see RDP. Let's say suppose I'll start it, right? I started it now. Let me do another scan. If we see 3389, that's how it's done here. We did not. We get it.
But that RDP will be your Windows IP, right?
John?
I think the remote desktop configuration which you are starting right now is the Windows IP, right? But in here you are checking for Kali and X IP, right?
No. I'm scanning this IP address.
Okay.
Yeah, I'm scanning remote. Remote calls. Remote desktop. Yeah, let me figure that out. I think the IP address which you're scanning is for, yeah, 21 the right one, but I am trying to locate. Can I? Remote desktop. Yeah, remote desktop service. It's running. Allow users to connect to remote desktop. Okay, this is done. Need to figure out what do I need to do to open this. I'll figure that out and let you know.
Sure, Kishore, sure.
Yeah. Okay. Perfect. Let's minimize that. Let's close this. Once again. No. Services.msc. So I think I ensured that machine is running. I need to go and close that off as well. I don't want to keep it running and then have you guys come back and log into the machine. Okay. URS, yeah. Up. 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 Down. Okay. So perfect. So now let's talk about the other topics, which is nothing but your domain name service, DNS. So DNS is nothing but DNS allows you to request a website basically, but all the websites are named, has got google.com or something like that. It's not IP addresses. It's all having conventional names, which you can understand. You can easily remember them. But how does DNS actually work? So basically what DNS does, it resolves the host names to an IP address and then vice versa, right? So the way you can't remember phone numbers on your phone and you save it with the name, DNS does the same thing, but it will search for that when you request that. So let's say suppose you say that I want to go to www.timesofindia.com. So what happens? It has got three different parameters here. www, which is the internet. Yes, I want to go to internet website, and Times of India, which is the actual website, and the .com, the actual domain where is it hosted. Like it's a commercial domain, a .com domain, correct? So in this example, if I'm looking at cobra.netlab.ohio-state.edu. So when this happens, what happens? It will go to the actual root server. So how the DNS architecture is set up is your organization or your ISP will have a DNS server. Every time you are trying to access a website, the request from your server or your machine will go to this DNS server, which will say, hey Kishore, thank you for giving me a request. I will take this request in and I will search the IP address of where is it hosted and let you know the IP address of that particular exact the server of IP address of the server where it's actually running, and then you can go and talk to it. So it takes the request on behalf of you, goes out and talks to other DNS servers. Hey, you know what, Kishore, I have got a request from for you. Can you find out what's the IP address for this particular website? And those DNS servers in turn will ask others. If they have information, they'll return it back. If they don't, they'll keep asking it back. So thereby, we have a concept of called recursive and non-recursive DNS servers. Recursive servers is repeatedly ask the question over and over again. Like, do you know? It will keep asking all the DNS servers in its circle that do you know what this IP address of this particular domain is. Non-recursive servers will only ask once. Did you know? And that's it. It will only talk to its external DNS server if it's hosted on the internet. And it says it will take the request from the internal machines and say that I have got an internal, I am the internal DNS. I will not talk to the internet. External DNS server for the company. You take this request, go and talk it. Just search about it. So you've got a recursive and non-recursive DNS servers which will do the querying of this IP address to hostname, hostname to IP address resolution. So in this case, your .edu, so we have got 13 primary domains, right? And then we have 13 root servers like these. So these root servers will have information about all the top level domains, which is .edu, .gov, au, us, .com, .in or something like that. So when you say that you want to access the .edu site, the root server will say that, okay, for .edu, please contact the .edu server or .edu root, subroot. So when you talk to edu root, he says, I want to look at .ohio state. He says, okay, the ohio state.edu site is hosted here. You go and talk to this person. So it will redirect to this particular state or this, give the IP address for this. When you go and talk to this, it says, okay, you are looking at NetLab. Okay, here is the NetLab domain or subdomain IP address. And when you talk to the NetLab will give you the IP address for Cobra. And this Cobra will directly talk to the actual endpoint saying that, okay, where the request came from, I will have to go and respond back to that particular person. So that's how your DNS actually really works in the real time. So when you say that this might be a lengthy process, how can I access google.com everything so quickly? So all this DNS data is being cached to your nearest DNS server of your ISP. So that the most frequently accessed websites, it's caching and it's identifying the IP. It's keeping a database of frequently accessed websites and the corresponding IP addresses, so that this querying time will get reduced. You'll access the data very fast, right? So the next slide will give you a representation of what happens. The number one, get the IP address for gohacking.com. It goes to a DNS server. The record for this domain doesn't exist in my cache, which is a kind of a storage of the table of the IP address to domain name. I will forward the request query to other server, which is the third DNS server for the ISP. So this DNS server will try to query on behalf of you, say that, okay, what is the, okay, so it is third server will say that, okay, thanks for letting, so I gives the IP address for the gohacking.com. It says this, the DNS server will say, thank you for giving me. I will also store this information in my cache and then provide the data to the, I think somebody's yawning. Who's that? Okay, so the actual source will say that, okay, thank you for providing me the actual IP address or the IP address. I will directly go and communicate with the gohacking.com. So this is how your DNS actually works, right? In a very nutshell. And then you have got your name resolution on the DNS name resolution. So you have got your primary DNS server, your name server, it has a cache, it has a database. The user will query the name resolver, which is nothing but your primary DNS name resolver or for that IP address. Yes, I want to query the IP address, query the IP address for this particular domain. The name server look up that, and it doesn't find it in the cache. It requests for other name server, the other name server, the other name server, and mix up the database server. So why do you say the name server? Name server is nothing but I'll tell you what I'll give you example for. Yeah, offsides. Yeah. So I say so guys, you can also register or save this rawtext.com. This is a very good site for you guys, for you to search a lot of data. So you see the name servers, name NS0, NS1 Yahoo, NS2 Yahoo, NS3 Yahoo, NS4 Yahoo, NS5 Yahoo. So these are all the name servers for Yahoo. Primarily, these are responsible for querying any incoming request, right? So this is how the IP address. So Yahoo is a big domain, so it has got 5 name servers for itself to go and resolve all the queries coming from different IP addresses. You'll see a lot of information here: the name servers, the mail servers, right? The records, the DNS records. Lot of information there, and then search engine optimization, Yahoo, common keywords, Yahoo mail phrases, what's ranking. You can trust the website or not. It's the Alexa ranking, whether it's what's the rank of this website. Alexa is not your Amazon Alexa. It's the Alexa which will rank the websites. Right? If you say Alexa top 1000 or Alexa top 100 websites, it will give you a top 100 websites of trusted websites. Right? And then you can find out a lot of information about Yahoo, like threat meter. What else did you see, or what does other people saw, or who was trying to use Yahoo for bad malicious purposes, and something like that. Right? So, yep, I think that's it. We have come to a conclusion for our networking concepts. I think the only concept which is remaining is a cyber kill chain, which I think I will try to talk to you about next week, if this is good with you guys, because I want you to be really fresh. Where do we start off? Any questions, guys?
Kishore, Aditya again.
Yeah.
At the start of the session, you asked a question, right? What is our home network topology?
Yeah.
So router will be in star topology. It's okay. But what about my which I connect only one? If I connect only one computer to the Wi-Fi, so
yeah,
will it be in star topology, or I said bus topology?
It will still be a star. See, the bus thing is you need to have a data cable connecting to that, right? So the one cable where everybody else taps in is what the bus topology is.
Okay.
Star is nothing but you are physically virtually and in a wireless manner also connected to one central router.
So no matter how many devices. Okay. Go on.
Yeah. So all the other devices will also connect to that thing only.
Okay.
Yeah.
So no matter how.
Sorry.
Go on.
No, sir, that's okay. Go on.
I'm saying that no matter how many devices are connected, but the topology is same.
The topology is same.
Okay.
It will be a star because everything is querying from client server, right? Everything is trying to query from your Wi-Fi.
Yeah.
Yes, so yes. So it's not that in the bus. What happens in the bus was you had a network cable and then everybody was there after you. So do you think if you are accessing internet, your sister, your brother, your parents will not be able to access internet? They will be able to, right? So it means they are independently connected to that router. They are not connected after you or before you.
Yeah.
Right? They are not in a sequence. So if you remember the bus topology, you had one backbone cable. Everybody was connected. And if you are sending and I am right next to you in the bus topology, if you are sending, I had to wait so that you finish your communication and then I use and I can send out the communication. But in the star topology, it's not like that, right? Star topology, everybody can send everything at any given point of time. The communication constantly goes on. Nobody is stopping you or nobody is trying to restrict you, right?
Yeah. So if I use only LAN, if I use from the LAN connection, so will it be like that?
No, LAN again. So that's what I'm saying. The current in the current generation, LAN will also be connected to a router.
Okay.
Right. So if you're sitting in your office or in a college, if you say that you are into R&D development or into biology lab or into computer science lab, so your computer science lab will be connected to a switch or a router which will go out and connect to the main internet connection, right?
Okay. Yeah.
Right. But you're still connected to the router, right? Every other machine is connected to the router in another way or form.
Yes.
So, but still, you are not waiting for your colleague or your fellow student to send out communication and your system says, hold on, you cannot send out the communication because your friend is sending out. No, you will be able to access browsing internet and others will be able to browse internet. So it all happens is you have your hub or switch or router in the main and you all are connected to that and that is connected to the ISP or the internet service provider.
Okay, sure.
And that's how you go. So remember the difference is in the bus topology, you have to wait before you have to check whether others are sending or not.
Okay.
If others are not sending, you can do it. If others are sending, you have to wait. But in this star topology, you can just send it.
Okay, okay. Sure, sure. Thanks, Ravi. Thanks,
Sure.
Kishore. And do you have any idea to, I mean, are you planning to provide any classes on cryptography? As you're saying so much in these networking classes, I thought that you
Yeah,
cover only basics. I mean, like saying that OSI layers, something like that, and just brush up the basics. But you are saying so much topics in this networking.
yeah.
So, are you planning on any giving any cryptography classes?
So cryptography is a broader sense. Yeah, I can give you, but I think that will be a different topic altogether. That's a whole lot logical topic because see, when I was doing my CISSP back in 2011, I read about encryption. Though I still read about it, when you have to start showing it, right, in a very logical sense, I have to start showing it to you because
Okay.
the moment I showed you an example, where was that example? Yeah, this one, right? ECB and CBC, it's electronic code book, and CBC cyclic CBC. I forgot. Yeah, I remember what is CBC encryption. Yeah. See, yeah, cipher blockchaining. So when I start explaining that, right, the whole conversation will go into a different channel at least.
Yeah, yeah.
I can show you examples of how this works. So if you want me to talk about this, and I can still talk to you about this one, but you'll not have a head and tail about it. So this is whole level of different topics which you will talk about encryption, decryption, how the encryption happens, how the decryption happens, what are the different protocols, how the ancient protocols were used, what is the current protocol level or the encryption levels are there. Yes, we can talk about it.
Okay, okay. Sure, sure.
Yeah, if you want, I can share you some material, and then if you have any questions, you can ask me. But probably not in this forum. We probably will not discuss in that depth. Yes, we will discuss, but not in that depth.
Sure, sure, Kishore. Definitely.
Then you have Ashish. Any questions from your end?
Sir, I want to ask that in cyber crime analysis,
Yeah.
how we can detect any crime in black marketing that level?
So I think that's a very broad question, Ashish. Let me try to answer that. So there are some data. So how do you think you will detect a thief in your house? आप चोर को कैसे पकड़ोगे घर में आएगा तो, राइट? क्या देखोगे घर में आएगा?
अब चोर तो अपने को यानी बता कर तो नहीं आएगा.
हाँ, मतलब दरवाजा तोड़ा होगा या फिर खिड़की टूटी हुई होगी.
Security cams.
Sorry?
Security cams.
Yeah, security cams. So, probably Aditya, you understand Hindi, right?
Bit. But I can't.
Yeah. Yeah, but you can understand, right? Okay, for Ashish's benefit, I'll give you an example. So आपको पता चलेगा कि गैप क्या है सिस्टम में, घर में क्या है, सामान टूटे हुए हैं, बिखरा हुआ है सामान जिस पोजीशन में रहना चाहिए उस पोजीशन में नहीं है. ये सब चीज देखिए आप आइडेंटिफाई करोगे कि कोई आया है मेरे घर में, कि मैंने चीज यहाँ रखी थी, यहाँ मूव हुई, कुछ प्रॉब्लम है. सिमिलरली हर नेटवर्क में, हर सिस्टम में थोड़े डेटा पॉइंट्स पे थोड़े की एरियाज हैं वेयर आप जाके चेक करोगे वो लॉग्स के लिए, राइट? सो एक सेकेंड, आई एम जस्ट ट्राइंग टू सो दिस इज, ये जो है आपका विंडोज इवेंट लॉगिंग है. यहाँ पर आपको सब टाइप के लॉग्स मिलेंगे कि मैं सिस्टम में कब लॉग इन हुआ, कब लॉग ऑफ हुआ. एक सेकेंड, ये लोड हो रहा है, गिव इट सम टाइम. Everything is going good. Okay, no problems. Perfect. Now we got it. Yeah. So ये जो विंडोज सिस्टम लॉगिंग है, इवेंट व्यूअर है, या यहाँ पे आपको हर चीज दिखेगी कि ये पर्टिकुलर इवेंट आईडी जनरेट हुआ सिक्योरिटी एसपीपी में, लाइसेंस एक्टिवेशन फेल हुआ मेरे सिस्टम में. ओके, सिक्योरिटी सेंटर डिफेंडर जो विंडोज डिफेंडर एंटीवायरस है वो अपडेट हुआ. So, हर चीज यहाँ पर रिकॉर्ड होती है हर सिस्टम में. So ये क्या था, एक सिस्टम ऑडिटिंग 5739. So क्या हुआ, enumerate credentials. Event source occur when a user performs read operation of stored credential manager. Right? Who did that? You know, desktop. This is my machine, right? Which is doing that. So अभी मैं जाके चेक करूँगा कि 4624 में log on हुआ. So somebody logged on to my workstation or I logged on to my workstation. What time? Right? Abhi, if I am looking at these details, I am trying to identify who's that, this machine, which service is running, कौन log on हुआ, special log on किसने किया, कि उसमें user ID क्या था, उसका privileges क्या था. So ऐसे these are all the parameters of the, ये पूरे identifications है कि कोई आ सकता है, कौन, अगर किसी ने log in किया है मेरे machine में without my knowledge, I can use these logs and write a rule to find out who was the one who logged in. These are called audit evidences. These are called audit logs. So हर system में audit logs होता है. And that audit log का job है कि it records every activity which is happening on your server, system, server, website, everything, everywhere. So when an attacker does something, we will try to identify what happened. So आप जैसे बोल रहे हो cyber crime हुआ है. So cyber crime कैसे होगा? Let's say suppose Paytm में cyber crime हुआ है या फिर Google Pay में cyber crime हुआ है. So Google Pay में cyber crime कैसे डिटेक्ट करेंगे? Google Pay में जब मैं एक्सेस कर रहा हूँ, Google के पास इंफॉर्मेशन होगा कि कहाँ से मेरा Google का IP आ रहा है, and then you know common IP addresses कहाँ से मेरा Google का Pay होता है, correct? So common identification points where my Google Pay connection will come from. Suddenly you see that Google Pay activity is happening from a different, from different state, and within a matter of minutes, like थोड़े समय के within half an hour मैं हैदराबाद में हूँ and मेरा एक और एक्टिविटी हुआ दिल्ली से. कैसे is it possible कि half an hour में दिल्ली पहुंच सकता हूँ? नहीं ना. Then Google वाले क्या करेंगे? It not alert that. You never know कि आपने credential किसको दिया. But when you report that मेरे पास कुछ ऐसा crime हुआ है, they'll go back and check when was the login activity came for a Google Pay account from your IP address or from your login, and where out the login came from. उस basis पे वो लोग try to triangulate करेंगे कि access कहाँ से हुआ और किसने access किया, किस IP address से आया, and then they will try to access and find out who did what. आशीष कुछ मतलब समझ में आया आपको? Did I answer that question?
Yeah.
Okay. Perfect, guys. Any more questions before we wrap up?
No questions, Kishore, from my side.
Super. Awesome. Thank you, guys. Thank you, Ravi.
Okay.
Thanks, Kishore. Thanks, Aditya. Thanks,
Kishore.
Ashish.
Thank you.
Thanks, sir.
Yeah, bye.